an earlier lecture, I had considered a composite system made of two oscillators. We wrote down the creation and destruction operators for one of the oscillators as A dagger and A respectively. And then for the other oscillator, we had creation and destruction operators, photon creation and destruction operators if you spoke about it in the language of photons, and ladder operators if you spoke about it in the language of simple harmonic oscillators. We call them B dagger and B, and they satisfied commutation relations. Commutator A dagger is identity, commutator B dagger is identity, all other commutators vanish. Now that was a composite system. It had two oscillators, and we used these operators to provide the angular momentum algebra. So we had J plus, the angular momentum raising operator, which takes the third component of angular momentum, increases it in steps of 1 at a time, and that was given by A dagger B. Its Hermitian conjugate B dagger A did the job of lowering the third component of angular momentum by 1. And then there was Jz, the Hermitian operator, which was A dagger A minus B dagger B, apart from a constant. So now I want to consider another physical situation where I would use two sets of operators, A dagger and B dagger. This is the quantum beam splitter. So I have this beam splitter, and it's quantum. In the sense, I'm going to talk of a device which is a partially silvered mirror, on which photons can strike either through this direction or from this direction. Any set of photons that strike on the beam splitter will be partly reflected and partly transmitted. Similarly, photons that come from here would be partly reflected and partly transmitted. Since the photons can come in either in this direction or in this direction and strike the beam splitter, A and B are called input ports. And then for the sake of nomenclature, I'd like to call this C and I'd like to call this D, and these are output ports. So there are two input ports and there are two output ports, and photons that come either in this direction or in that direction get partially transmitted, partially reflected. So that is the picture that we have of the beam splitter. The photon creation and destruction operators for photons that travel in this direction are given by A dagger and A respectively, and they satisfy this commutator algebra. Similarly, we have B and B dagger here. The beam splitter itself does the operation of partly transmitting and partly reflecting the photons. The operator is represented by B. This is the beam splitter operator, and B is a unitary operator given in this fashion. Normally, we associate cos theta with the extent of reflection, which I call R. So the extent of partial reflection, R, is simply denoted by cos theta. Notice that A dagger B minus B dagger A is anti-Hermitian. Is minus A dagger B minus B dagger A, and therefore B dagger is e to the minus theta A dagger B minus B dagger A. This clearly means that B B dagger is identity and it is a unitary operator. What is the action of capital B on A dagger, little b and B dagger? Now, this we can find out easily because we know that unitary operators act in the following manner, taking it to a new operator. So, we can compute B A B dagger, capital B, little b, B dagger and so on. So, we first do that. I want to emphasize the fact that this theta has nothing to do with the geometry of the beam splitter in general. It has to do with the extent of partial reflection. So, now I wish to find out B A B dagger. I have deliberately avoided putting these overhead caps on top of B A and B dagger. So, we need to compute this. Of course, I will use the Baker-Campbell-Hausdorff formula, and this would just be A plus commutator of theta A dagger B minus B dagger A with A, and suppose I call this commutator P plus theta A dagger B minus B dagger A with P by 2 factorial plus so on. So, let us first write this down as A plus theta. The first term is commutator of A dagger B with A, which gives me a minus B. The second term vanishes because A commutes with itself. So, this is P. This whole object is P. So, I need to find plus theta by 2 factorial minus theta B with A dagger B minus B dagger A. With minus theta B, so let me write minus B out here and so on. So, this is A minus theta times B plus or minus theta squared by 2 factorial. The first term does not give me anything. I have put minus theta squared there. The second term will give me a 1, and therefore, that multiplies A and so on. Now, we can write out all the terms, and it is easy to check that B A B dagger is simply A 1 minus theta squared by 2 factorial plus theta to the power of 4 by 4 factorial plus so on, minus B theta minus theta cube by 3 factorial plus the rest of the sine series. So, this is A cos theta minus B sin theta. Similarly, we can compute B small b B dagger, and that object is just B plus theta A dagger B minus B dagger A commutator with B, and if I call this Q, the next term is plus theta by 2 factorial theta squared by 2 factorial commutator of A dagger B minus B dagger A with Q and so on. Now, this object is just B. It is only the second term that contributes, and that gives me a plus sign plus theta A. This gives me a theta squared by 2 factorial commutator of A dagger B minus B dagger A with A. It is easy if we do this series expansion to see that B small b B dagger is B sin theta, B cos theta plus A sin theta. So, this is what we have for the action of the beam splitter. So, let me put that down. I have B A B dagger is A cos theta minus B sin theta. This is the effect of the beam splitter on A, and therefore, B A dagger B dagger is A dagger cos theta minus B dagger sin theta. I can take the Hermitian conjugate, or I can work it out again once more, and this is what I would get. Similarly, this object is A sin theta plus B cos theta, and B dagger, capital B dagger, is A dagger sin theta plus B dagger cos theta. So, this is what we have. Now, a 50% beam splitter is one which sends 50% of, transmits 50% of the intensity of the light. Of course, if it comes from this port, it transmits 50% this way and reflects 50% that way. And therefore, for a 50% beam splitter, cos theta is 1 by root 2, and so is sin theta. I just have the following: A dagger minus B dagger by root 2, and similarly, this object is A dagger plus B dagger by root 2. So, these are basic preliminaries that I need in order to see what happens to various photon number states which are put through these input ports. As you can see, this is a unitary transformation that is being done on A's and B's, little a's and little b's. The upshot of the whole thing is the following. Suppose in terms of states, I sent 0 photons through the input port A and 0 photons through the input port B. My initial state is simply 0A direct product 0B, and you will recall that in my notation that is the same as 0A 0B, and it would also be the same as 0 0. So, these are just various shorthand notations that I would use, but in any case, if the input is 0 photons through the port A and 0 photons through the port B, you do not expect to see photons in the output ports. So, you would expect 0 photons in port C and 0 photons in port D. So, basically 0A 0B goes through the beam splitter to give me 0C 0D, and that is common sense. Now, I will use this fact. Suppose I have 0 photons through the port A and 1 photon through the port B. I can well write this as 0A, B dagger 0B, but that is the same as B dagger 0A 0B. Remember that this is a product state here, and B dagger acts only on ket 0B and leaves 0A untouched. This is passed through the beam splitter. Now, I can look at this situation from the framework of the output ports C and D, in which case I need to write B dagger in terms of C dagger and D dagger. And what are C dagger and D dagger? B A dagger B dagger is A dagger minus B dagger by root 2, I am going to call that C dagger, and B B dagger B dagger is A dagger plus B dagger by root 2, and I call that D dagger. Now it is important to check if indeed we have done a unitary transformation. In the sense, is the algebra preserved? So I need to check the commutator of C with C dagger. C with C dagger is simply half A with A dagger, which is 1, and then I have B with B dagger, and that object is simply going to give me a commutator 1. So I have A minus B with A dagger minus B dagger by 2, and that is what I have written there as 1. Similarly, D with D dagger in the commutator is 1, and therefore I know that I have gone from the algebra A dagger is 1, B dagger is 1 in the commutator algebra, to C dagger commutator is 1, D dagger commutator is 1. So I can well look at this state ket 0A 1B, which I have written in this manner, from the point of view of the output ports, which means I write B dagger in terms of C dagger and D dagger. Of course, ket 0A, ket 0B is identified with ket 0C, ket 0D. That is what happens if you send nothing through the beam splitter. I can solve for B dagger and A dagger from these equations, and then I can put in the expression for B dagger there. So I have C dagger is A dagger minus B dagger by root 2, and D dagger is A dagger plus B dagger by root 2. So I can substitute for B dagger and get my answer here, and therefore I have this object to be given by D dagger minus C dagger by root 2 0C 0D. But I know what this does. I merely have zero A 1B is the same as D dagger, that was my input state. This goes to D dagger minus C dagger by root 2 0C 0D, but that is 1 by root 2. The first term is D dagger acting on 0D, giving me 1D, leaving 0C alone. Then the second term is C dagger acting on 0C, leaving 0D alone, and this is what I get. Now, this is a very interesting and important result, because it tells me that if I had sent in 0 photons through the input port A and 1 photon through the input port B, I might expect to see the single photon that I sent in through the input port B either coming out through port C or through port D. But this tells me that there is a 50% probability that it comes out through port D and 50% probability that it comes out through port C. This is a very interesting result. So it looks like the probability is really divided between port C and port D. I could see the single photon here 50% of the time, or in port C 50% of the time. So this is an interesting result, and it has come about because of superposition. Now let us look at a situation where we have 0A or 1A 0B. I could repeat this argument. 1A 0B is the same as A dagger on 0A leaving 0b alone, and writing A dagger in terms of C dagger and D dagger, that is the same as A dagger minus B dagger by root 2 is C dagger, and therefore A dagger is C dagger plus D dagger by root 2 acting on 0A 0B. So this is what happens when it goes through the beam splitter, and this is the same as 1 by root 2, but 0A 0B is the same as 0C 0D, and therefore this gives me 1C 0D plus 0C 1D. Once more, I have verified that if I had sent a single photon through the input port A and nothing through the input port B, there is a 50% probability of seeing the single photon either through the output port C or the output port D. Now let us look at a slightly more complicated situation. By way of exercise, let us consider an input state 0A 2B. I would write this as 0A. When B dagger acts on 0B, it gives me 1B, and when B dagger squared acts on 0B, it gives me root 2 2B, and therefore I will write 0A 2B as ket 0A 2B apart from a root 2, so this is what I have. Now this object can well be written as 0A 2B after beam splitting goes to 1 by root 2. I will have to write B dagger squared in terms of D dagger and C dagger, and therefore I have D dagger minus C dagger by root 2 twice D dagger minus C dagger by root 2. So this multiplies that. 0C 0D, because I have used the fact that 0A 0B is the same as 0C 0D. After beam splitting I get nothing. So this is 1 by 2 root 2 D dagger minus C dagger. The first time this D dagger minus C dagger acts on ket 0C ket 0D, I get 0C 1D minus 1C 0D. Now once more it does the job, that is 1 by 2 root 2. The first term gives me 0C, D dagger on 1D gives me root 2 2D, C dagger on 0C gives me 1C and leaves the 1D alone. When D dagger acts on this term, it gives me minus 1C 1D, and of course there is a C dagger which acts on this, which gives me root 2 2C 0D. Of course I can add these two terms and put a minus sign out there, and this is what I have. So what does that tell me? It tells me that if I had sent 2 photons through the input state, there is a non-zero probability of finding 2 photons in the output port D, or 2 photons in the output port C, or 1 photon in each of the output ports. The photon number is conserved, it needs to be conserved in any case. We should also check that the total probability is 1, and that happens really because the first term comes with the coefficient half, that is the probability amplitude. that gives me a probability quarter for 0C 2D, similarly a probability quarter for 2C 0D, and a probability half for 1C 1D. Therefore, the total probability of finding the photons in the output port happens to be 1, which is the way it ought to be. So, this is what I have if I send 2 photons in. It is easy to generalize this to n photons through an input port. This also tells us about the power of the vacuum state, because despite the fact that nothing was sent in through port A, you find that the output ports have a certain distribution of photons. There is a non-zero probability of seeing the photons in both C and in D, and that is because of the power of the vacuum, Ket 0A. A very interesting and important result now, where we simply look at a single photon going through each port. So, let us look at this state, 1A, 1B. Now, as before I write this as A dagger 0A, B dagger 0B. So, after passing through the beam splitter, I substitute for A dagger and B dagger in terms of C dagger and D dagger. So, A dagger is simply C dagger plus D dagger by root 2, and B dagger is D dagger minus C dagger by root 2, and this acts on 0 C, 0 D, and that is a half C dagger plus D dagger. The action of D dagger on 0 C 0 D is 0 C 1 D. The action of C dagger is 1 C 0 D. Now, once more, the action of C dagger on the first term is 1 C 1 D, and on the second term is minus root 2 2 C 0 D. That is very nice. Certainly, I am conserving the total number of photons, that is a 1 plus 1, and this is a 2 plus 0. But now look at this, D dagger on this gives me a root 2 0 C 2 D, which is fine, and then the last term is minus 1 C 1 D. There is a cancellation between these two terms, and I just have my final answer as 1 by root 2 0 C 2 D minus 2 C 0 D. There is 0 probability of seeing a single photon in the output port C and a single photon in the output port D. And this is an important statement, because at the face of it, we might imagine that given 2 photons, as in the earlier example, I should be able to get a term which says Ket 1 C, Ket 1 D in my final state. But such a thing is missing, and this is what I have. Both the photons are seen either in the output port D or in the output port C. Now, let us consider another situation where I send a coherent state through one of the ports and the vacuum in the other. So, my input state 0 A alpha B. Just by way of recapitulation, alpha is any complex number. In the Fock state representation, that means in terms of the photon number states, this is written as follows. And therefore, it is an interesting quantum superposition of the 0 photon state, the 1 photon state, the 2 photon state, and so on. This is a normalized state. You can get it from the vacuum by the action of the unitary operator d of alpha, where d of alpha itself is e to the alpha a dagger minus alpha star a. Further, alpha is an eigenstate of the annihilation operator A with eigenvalue alpha. Recall that the 0 photon state is also an eigenstate of A, but with an eigenvalue 0. That is a non-trivial state, eigenstate of A. Further, alpha beta is not equal to 0, where beta is another coherent state. So, this is what we had shown earlier. So, now let us consider this input state. D of alpha itself is a unitary operator. Satisfying d dagger of alpha is d of minus alpha. So, now I have an input state 0a alpha b, and this is passed through the beam splitter. I can write this as 0a d of alpha acting on 0b. By 0b I mean the vacuum state through the input port B. So, but that is the same as d of alpha 0a 0b, ket 0a ket 0b. But this is e to the alpha a dagger minus alpha star a ket 0a ket 0b. I know what happens to a dagger and a, and how they appear if I look at it from the framework of the output ports. I know that a dagger is c dagger plus d dagger by root 2, and a is c plus d by root 2. Now, incidentally, this is just using the disentanglement formula. This is e to the minus mod alpha squared by 2, e to the alpha a dagger, e to the minus alpha star a, acting on 0a 0b. So, this basically, once it goes through the beam splitter, it is e to the minus mod alpha squared by 2, e to the alpha a dagger is c dagger plus d dagger by root 2, minus alpha star e to the minus alpha star a, and this acts on 0a 0b, but that is the same as 0c 0d. Now, I am looking at the whole thing, at the whole system from the point of view of the output ports, that is in terms of operators c, d, c dagger, d dagger, and the basis states there, that means ket 0c, ket 0d and so on. So, this is what I have. Now, of course, I need not even have disentangled this. I could have just written this in toto as e to the alpha c dagger plus d dagger by root 2 minus alpha star c plus d by root 2 without using the disentanglement theorem, acting on 0c 0d. And then I can group terms in the exponent, which is what I will do now. So, 0a alpha b passes through the beam splitter and looks like this: e to the alpha by root 2 c dagger plus alpha by root 2 d dagger minus alpha star by root 2 c minus alpha star by root 2 d 0 c 0 d, and I can combine terms in the exponent and write this as e to the alpha by root 2 c dagger minus alpha star by root 2 c, that is the first term, plus alpha by root 2 d dagger minus alpha star by root 2 d. That is the rest of the terms in the exponential acting on 0 c 0 d. This is an interesting structure because this is like d of alpha by root 2, and that is another d of alpha by root 2, except that this corresponds to the operator c dagger and that to the operator d dagger. It is also true that these two objects commute with each other because c and d commute with each other. And therefore, I can now use the disentanglement theorem, and I just can write this as e to the alpha by root 2 c dagger minus alpha star by root 2 c, e to the alpha by root 2 d dagger minus alpha star by root 2 d acting on 0 c 0 d. Well, that is just going to give me, when this object acts on 0 d and this object acts on 0 c, that just gives me alpha by root 2 c alpha by root 2 d. In other words, I started with a coherent state going through one input port and ket 0 in the other. The output ports have two coherent states, but instead of the original alpha, it is alpha by root 2 sitting in each of these kets, inside each of these kets, and therefore, the intensity of the coherent state has gone down. Remember that the expectation value of the photon number operator in the state alpha is mod alpha squared. Therefore, now the intensity has gone down. Instead of alpha, I have alpha by root 2, and therefore, in this state, the expectation value of A dagger A has come down. It is half the intensity here and half the intensity there. By intensity, I mean the number of photons, the expectation value, the mean photon number. So, this is what I have. So, the power of the vacuum is again well demonstrated because it helps you to produce two clones of the original coherent state. Initially, I had one coherent state, but now I have two of them, each one in one of the output ports with the intensity down, but still the coherence properties are preserved. So, that is one of the uses that I have when I send ket 0 through one of the input ports of the beam splitter and ket alpha through the other input port of the beam splitter. Finally, let us look at the following situation: alpha A, beta B, where alpha, beta are complex numbers. Ket alpha is a coherent state, ket beta is another coherent state. So, I have sent in two coherent states, one through each of the input ports. And so, what do I have by way of output? So, this can be written as d of alpha, d of beta, 0 A, 0 B. So, this is passed through the beam splitter. By way of output, I have the following. This object is e to the alpha A dagger minus alpha star A, e to the beta B dagger minus beta star B, 0 A, 0 B. Once more, I can write this as e to the alpha A dagger C dagger plus D dagger by root 2 minus alpha star C plus D by root 2. That is my first term. Then I have e to the beta B, which is beta D dagger minus C dagger by root 2 minus beta star D minus C by root 2, because B dagger was D dagger minus C dagger by root 2. I have just put that in. Ket 0 A, ket 0 B. Now, it is clear that these two objects do not commute with each other. But I could use the following. I could use the fact I can now group terms, for instance. This is e to the alpha by root 2 c dagger minus alpha star by root 2 c plus alpha by root 2 d dagger minus alpha star by root 2 d. That is what I have in the first exponent. The second exponent has e to the beta by root 2 d dagger minus beta star by root 2 d plus minus beta by root 2 c dagger minus beta star by root 2 c, and this acts on 0a, 0b. I can use the disentanglement theorem. I know, for instance, that this commutes with this because this is just a function of c and c dagger, that is a function of d and d dagger, and they commute with each other. Similarly, this term commutes with that term. Now, if I did that, I would have the following. Out here, in fact, once I do the disentanglement and I combine things, I should be able to get alpha minus beta by root 2 c dagger minus alpha star minus beta star by root 2 c, that will be one term. Then I have alpha plus beta by root 2 d dagger minus alpha star plus beta star by root 2 d, that would be the other term. So, already I can see where it is going, but I am going to pick up some phase factors. I use the fact that d of alpha, d of beta is e to the I imaginary part of alpha beta star, d of alpha plus beta. So, this is a crucial input because this is e to the alpha a dagger minus alpha star a, e to the beta a dagger minus beta star a, and then that quantity can be written in terms of the right hand side suitably. So, out here, first of all, I use the disentanglement theorem, and this can be written as I initially started with alpha a beta b, went through the beam splitter to give me times e to the alpha by root 2 d dagger minus alpha star by root 2 d. These two commute with each other, so I can well split the exponent like this. Similarly, there I have times e to the beta by root 2 d dagger minus beta star by root 2 d times e to the minus beta by root 2 c dagger minus beta star by root 2 c. I can well write it in this fashion, acting on 0 c 0 d. We can now group terms suitably. For instance, these two quantities can be combined. I have an alpha by root 2 d dagger minus alpha star by root 2 d, beta by root 2 d dagger minus beta star by root 2 d, and therefore, using this trick I can combine them. This object is d of alpha by root 2 and this is d of beta by root 2. Similarly, I can combine these two terms, this commutes through this, through that out here, and therefore, I write the following: alpha a beta B goes through the beam splitter to give me e to the alpha by root 2 c dagger minus alpha star by root 2 c e to the minus beta by root 2 c dagger minus beta star by root 2 c times, I maintain this order, e to the alpha by root 2 d dagger minus alpha star by root 2 d times e to the beta by root 2 d dagger minus beta star by root 2 d. And this acts on 0 c 0 d. I can now combine things and see very easily that this is to be written as d of alpha plus beta by root 2. The first term is alpha minus beta by root 2. Then there is an alpha plus beta by root 2. Zero c 0 d. There is a phase out here because when I add the two of them, this is d of alpha, d of alpha by root 2, d of beta by root 2 is d of alpha minus beta by root 2 minus sign coming from here times an overall phase which is e to the I imaginary part of alpha beta star. But I pick up exactly e to the minus I imaginary part of alpha beta star from here, and so the phase factors, those extra phases cancel out, and this is what I have. But this is precisely the coherent state and therefore, when I send in two coherent states, ket alpha through one and ket beta through the other, I get two coherent states in the output ports, one in each port, one of them being alpha minus beta by root 2, the label is alpha minus beta by root 2, and the other's label is alpha plus beta by root 2. So once more the coherence property is preserved, except that there is a change in the intensity of the state, and I get precisely this kind of combination which leads to a different intensity compared to the original intensity of the states. So this is the setup in which a quantum beam splitter is used. One of the main advantages is that you can produce copies of coherent states. You will recall that if I had the vacuum in one of the input ports and a coherent state in the other, I finally get two coherent states. So I can produce two copies of a single coherent state. Further, if I started with two coherent states, the output ports also have a coherent state in each of them, except that the intensity is different. These are the ways in which a quantum beam splitter can be used. And this is another example of a system, a physical system, a very relevant system, where I play around with two sets of operators, A dagger and B dagger, and produce some very interesting results.